I'm not crazy, I'm not crazy, I'm just broken, not too many. Devotion, 1, 2, 3, listen to me, the voices in my head. I'm the pictures run. 1, 2, 3, the harmonizing voices in my head.
Uh, uh, ba, 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 ba.
Huh. Hmm. Ah, nice. Mm.
Hello, non-existent audience. This I, Sandeep from Half-Hour TV. And if you have no idea what Half-Hour TV is, it's a community of robotics enthusiasts who build and collaborate together. Our current project that we are collaborating on is a reinforcement learning based robotic arm that can segregate objects. But we are not here for that today. Today I'll be going on a solo journey through reading and understanding and potentially implementing this research paper. If you did not attend the last session, what this is the paper is implementing a singular formula that could, in theory, uh, enable any legged robot to traverse through any given environment. That was a huge deal back when the paper was released. This paper was released about 8 years ago, I think, and since it's been used by a shit ton of other papers and actual industry standards. So, yeah, they implement a single formula that determines a gate sequence meaning which leg moves first and the order of leg movement, step timings meaning the amount of time a particular leg remains in air or in contact with ground. Footholds refer to the location where a foot needs to land. And then swing leg motions, that's pretty understandable. 6D body motion. 3 for orientation, 3 for position over non-flat terrain without any addition modules. Yeah, the way they do this is they focus on the center of mass of the robot rather than the individual legs, and exactly how is still pretty unknown to me. But yes, I have had a meeting with my professor regarding this, and she has let me on a great deal of things which did not make sense initially. So, what traditional optimization techniques do is try to find the most optimal solution of a given objective function. Objective function meaning uh, a function that relates all the parameters of the robot in a way that when we maximize or minimize that function, we have found the desired values of the parameters. And instead of using the objective function and then having constraints that define the decision variables, what this paper essentially does is focus on the constraints themselves, find a feasible region, and only find a good enough solution. Because when anything involves real life, it's going to be complex. The paper doesn't work on linear problems, it works on non-linear problems that range from quadratic to even more complex. And given that we are simultaneously optimizing on so many parameters, it's basically impossible both on the resource management side and also the fact that these parameters are going to be determined on the go. These will not be predetermined because you can't really find out the footholds prematurely. That would require scanning the entire environment, which we are abstaining from. We are assuming that we are going over unknown terrains. The system represented using a simplified centroidal dynamics model, yeah, is what I was talking about. Uh, they are simplifying the system down to its center of mass, which is influenced by the field's location and forces. That way, we can actually formulate a singular equation rather than having multiple equations for each foot. We explicitly enforce friction cone constraints depending on the shape of terrain. This is something I haven't quite grasped on yet. The NLP solver generates highly dynamic motion plans with full flight phases for, yeah. So another issue that they dealt with is initially a lot of papers that involve gate sequences took an integral approach, like like they discretized the sequences in a way that they could just find out, like they could just define foot 1, foot 2, foot 3, and foot 4 in a particular order, or maybe sometimes even hard coding them. However, once you try to optimize any integral problem, you realize that there are a hell lot of parameters, and because there are a hell lot of parameters, there is an exponential amount of possible configuration of the legs. Like, we are not just dealing with the gate sequences, we are dealing with the footholds and a lot of things that are tied to them, and that poses a very big issue that can't really be solved by pre-made solvers. And that's basically why they found a way to make that discrete decision continuous in the, like, what I mean by that is they created a kind of piecewise function that would tell you what leg is what a particular leg is doing at the moment. They define two states for each leg, swing and then stance. Swing meaning the foot is in the air, stance meaning it's touching the ground. And they had a phase parameter, like a delta t phase parameter, that when put into that function that they derived would give you the state of the robot, like the robotic legs essentially. And because that would generate direct equations that could be fed into an NLP solver. So that is how the NLP solver generates aerodynamic motion plans, blah blah blah. We validate the feasibility of general plan simulation. Yeah, that this is the implementation part, which I won't be getting to until a month, I guess, or even more, because I have to cover robot kinematics and dynamics, and then optimization techniques, etc. And that shit is really heavy. Okay, so I guess before I get into the kinematics, I should just read through the introduction a little bit until I reach the kinematic model. The reason being the dynamic model is not in my ability to understand as of now, but we'll get there. Uh, yeah. So I'm just gonna read a bit, and then I'll get back to this. Yeah. A force can only be generated if the foot is touching the environment, or feet can only push into the ground, not pull on it. These are the few constraints and assumptions that they took, and this is the main reason that they chose the two states of the legs, swing and stance. Essentially, that divides the problem into two subparts. One where they deliberately have to swing the leg with the help of motors, and then second phase, the contact phase, where they have to carefully plan given the contact force restrictions and essentially kind of make each leg jump in a way using the contact forces with the ground. I don't even know exactly how trajectory generation works. It's something that Said Biniku deals very later on in the chapters. So it's a good thing that they use more automated methods and not go into detail of exactly how that works here in the paper. I hope not too much of the stream was missed. Oh no, oh well, no. A lot of frames were dropped. Ah, shit. Hmm. In case not a lot was recorded, I'll just give an simplified overview of everything I dealt with. The paper makes a single formulation that can determine in what order the legs of the robot move, the amount of time they stay in air or are in contact with the ground, where the foot needs to land, the motions of the leg while they're swinging, the motion of the robot body over any terrain. So we are dealing with a formulation for any legged robot over any terrain that's unknown. So we are not pre-assuming a particular terrain. This paper is pretty foundational given the fact that it was released about 8 years ago and since been used in a lot more papers. I see a moth banging on my window. Brother, go home. Uh, so instead of focusing on the legs it's themselves, because that would create like a million parameters that we have to deal with, instead we use the center of mass of the robot as the main parameter, and we make sure that the center of mass later on is linked to the robot leg parameters. So for optimization purpose, we only use the center of mass as the decision parameter, basically, decision variable. Hmm. And yeah, the paper does divide the motion of the legs into two parts, that is swing and stance, because this a force can only be generated if the foot is touching the environment or the basically presume constraints that are, I mean, these are quite obvious, right? And in order to feed those constraints, we need to divide the motion into two states. So we have sub problems like when the robot's leg is in the air, we need to drive it using motors and then generate a swing motion. But then if it's touching the ground, we need to take in the contact forces as the parameters as well. So both of those states are essentially different problems. The paper then talks about existing approaches, and this approach is very close to what we are doing in the paper itself. Linear inverted pendulum model, which basically,
Yo,
yo,
कौन सी पढ़ रहा भाई?
I'm going over a research paper.
हाँ, continue, continue.
Yeah. Hmm. The major disadvantage of this particular model is they are presuming the footholds, which mean the points where the robot's leg needs to land on and the step timings. But as the major fundamental is the same. Yeah, using the inverted pendulum model, we can use the center of mass as a parameter, which in turn depends on the robot legs, which in turn depend on the contact forces, rather than directly using the contact forces, which would lead to like a million other parameters. Yeah, but it is effective, I suppose, because it's being used in real hardware. If it was a relatively flat terrain, then it wouldn't be much of an issue because we could directly just define where the footholds are. But on a non-flat terrain, it's basically impossible for us to determine where the feet needs to land beforehand. Yeah. Well, this point is related to the fact that we're using a linear motor pendulum model. This model assumes that the vertical height of the COM is fixed. However, that does restrict the robot by a lot. So instead of that, we need to essentially find a way to generate more complex motion involving vertical movement. Yeah, what people don't realize is if we did take the full dynamics in consideration, the actual dimensions or the actual degrees of freedom would be a whole lot more than six. And that's one of the reasons that we need to find a way to use the COM as a decision variable rather than the exact joint variables of every single leg. Yeah. What the fuck is Coriolis forces? Yo, Izito,
Hello.
do you remember anything
No,
about Coriolis forces?
there was something like that in 12th, no way.
Yeah, I think we learned that in geography related to something it's something
Oh,
related to inertia, I suppose so. If let's the
searching for the different topology.
or maybe it's the fact that when like a body rotates,
Yeah,
then the apparent like outward forces that is felt by people standing on that object, I think is that.
yeah, I guess the example, the video where they're demonstrating the like two people are sitting on a rotating disc and they throw a ball or something. There's something like that. But
Oh,
in this case, the moving disc is the planet and it's deflecting the object which enters the uh, orbit. Yes.
say I kind of understand what you mean.
Well, right now I'm reading the book. I'm on Euler's equation.
Bro, damn.
Oh, Euler's angle. Euler's angle. Nah,
Oh, okay.
the
So I'm
derivation is so hard, man. Like it's taking some time, man. Deriving every single thing, yeah, it's a lot of time. Oh, we are roughly on the same page, I guess. I'm done with the
yeah.
RPY. Second was the Euler's angle.
I did go through this part once previously, but
Yeah,
I think I don't really remember anything from this.
yeah. I actually also go through this once, and then I gave up halfway, and then I started again today. And after reading it for a while, I guess I got it. Like
Yeah, what the fuck
I
is
watched few
this?
videos on it.
What the fuck is
Yeah,
this?
yeah. I actually easy है. लाइक बेसिकली ये जो रोटेशन ए कॉमा अल्फा ए है ना तुझे 4x4 वाला मैट्रिक्स लेना है.
Oh, okay.
हाँ
So
एंड लाइक
basically
लाइक इन
individual
सब
rotations.
यस 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 उनका क्रॉस प्रोडक्ट करना है मतलब वो 4x4 है एंड उसका मल्टीप्लिकेशन करना है जैसे क्रॉस प्रोडक्ट हम करते हैं
Got it, got it, got it.
मैट्रिक्स वैसा ही है बट यूलर्स में ना पता नहीं गलत हो रहा है कुछ तो एंड लाइक पता है द मोस्ट बेसिक मिस्टेक आइदर वाज कि जो y जब लेते हैं ना हम रोटेशन ऑफ ओ थी थीटा हो, देन उसमें जो साइन का है ना, वो रोटेट होता है। बेसिकली
uh,
नॉर्मल एक्स एंड वाई के लिए ना वो सेम रहता है, मतलब अ, कैसे बताऊं भाई, मैं एक सेकंड सोचने का। लाइक भाई देख, जब तू डिराइव करे तो समझ में आ जाए मैं क्या बोल रहा हूँ, मतलब
got
वो
it.
साइन की वजह से ना बहुत ऊपर नीचे होता है यार। Like, उस वजह से
Yeah.
ना मेरा साइन में थोड़ा सा इश्यू आ रहा था, मतलब कैलकुलेशन सही थी, बस ये साइन में मिस्टेक आ रहा था मेरा।
You
देन
know,
आई गॉट टू नो कि हम्म
in our university we have a robotics minor, and the robotics minor just started like a few days ago. And the first
oh,
thing that the people were taught was, I think, degree of freedom and the basic like transformation of matrices part. And after reading through that, a lot of people just mutually exchanged their minors. Like they just moved away from robotics.
oh damn, like you are ahead of a lot of people right now, it's crazy.
Hmm.
Yeah, yes, robotics is kind of hard, but it is at the same time it is interesting, man. And
Wait,
ई
aren't you
यंत्र में
like aren't you
what
like a
आर
fresher?
एंड एक से मेरे सुनाई दिया वापस से, थोड़ा जोर से बोलो ना।
क्या आप ऑलरेडी फिलहाल फ्रेशर नहीं हो?
एक सेकंड, मुझे आवाज कम आ रही है ना, वापस से।
क्या आप ऑलरेडी फिलहाल ट्वेल्थ में नहीं हो?
नहीं भाई, मैं 12th हो गया, मैं अभी फर्स्ट ईयर में जाऊंगा। मैं
हाँ,
एमएचसीसीटी के थ्रू जा रहा हूँ। तो इसका रजिस्ट्रेशन हो गया है मेरा, मतलब
या
अभी कैप राउंड चालू है हमारा।
ओ
तो इसके 5 राउंड होंगे, और इसका फाइनल राउंड खत्म होगा 5 सितंबर को।
हम्म
एंड देन मेरा कॉलेज शुरू होगा, तो बहुत टाइम है मेरे पास। तो जब तक मैं ये बुक तो कंप्लीट कर लूंगा भाई मिनिमम, नहीं तो मैं रो दूंगा।
given that you are way ahead than me, I guess. Because I mean you have
ना,
a year's worth of advantage.
well, I was inspired by you, brother. So yeah, man. Thanks to you, I'm doing this.
Damn, thanks.
Yeah, man. Like I honestly saw how much you are putting efforts to into it, and then I thought I should do the same. Like I had the same motivation, but I wasn't doing anything to like show that I am interested or I want to
uh,
pursue it. So yeah, man.
honest
After looking
yeah.
at you, I am in the right direction, I think.
And also for me, the most major inspirational people were the initial ones like Justin and Isaac and even Tyan, because those people just
Yeah.
started doing crazy shit right from day one.
Yeah, the 8-bit moon also.
Yeah,
Crazy guy.
casually implements the entire thing,
Crazy man.
then calls himself lazy.
Nah, respect, man. Seriously, respect. Like the one more guy भाई, वो पता नहीं 18 घंटे से खेल रहा था गेम, इतना इंटरेस्टिंग तो गेम भी नहीं था। 18 घंटे से खेल जैसे रहा ही है। What was his name? 1 second.
Masao?
I don't think Masa was playing. Someone other guy actually. 18 घंटे brother. 18 hours straight. Who was it? Only you, Raj. Maybe that, yeah. Crazy man. 18 hours straight.
गेम खेल रहा था फिर लाइक स्ट्रीम कर रहा था?
नहीं नहीं, गेम खेल रहा था, सिंगुलैरिटी नाम था।
वो सिंगल।
नहीं मतलब वो स्ट्रीम नहीं कर रहा था, मैं वैसे ऐसे ही लोग देख रहा था, एंड लाइक मैंने जैसे ही उसको देखा तो भाई 18 आवर्स से वो एक ही गेम खेल रहा है। आई वाज लाइक क्रेजी भाई, इतना तो मैंने भी नहीं खेला भाई, ये चल रहा
डेडिकेशन।
है। Crazy.
डैम। Inverse kinematic solution for RPY
Yeah.
is more complicated than the spherical coordinates. Oh, okay.
हाँ, actually, because there are three. Yeah, brother, everything is hard. Nothing is easy.
Isn't the RPY coordinates basically the articulated coordinates? Because I think the articulated coordinates operates on the same principle as well.
Uh, Kinda no, actually. Like, there are three different angles, and in this one, there are couple. Basically, one will rotate, another will also rotate, and third will also rotate with respect to each other. Kind of like that. And they are like rotating at the end effector, not at the initially. Whereas
Oh, so
the
basically RPY is with reference to the reference frame.
end effector, like basically the hand of a robot.
Oh,
So
oh, and
like
then
this
articulated one is basically like
for the entire
they
frame.
happen
Yeah.
at, yeah, they happen at specific. No, wait, I think I'm fucking something up.
The this RPY is also used for like aeroplanes and shit. Like they use it for the controls of it.
Also, like for adjusting the final orientation of the end effector, right?
Yeah, yeah, yeah.
Got it.
Very interesting. The same, basically RPY and Euler's are basically the same thing, but the only difference is that uh, in RPY they are rotating for all the angle, whereas in Euler's uh, it is rotating for only two angles. Like it will rotate for one side, then other, and it will rotate once again for the first angle. मतलब जिस angle से आपने पहले rotate किया ना उससे ही आप ending में भी rotate करोगे. तो उस वजह से जो आपका एंड पॉइंट आएगा वो पैरेलल होगा आपके ओरिजिन से.
Initial, okay, got it.
लाइक बट इसमें assumption हम ये ले रहे हैं कि पहले से ही वो पैरेलल है, मतलब इन बोथ आरपीवाई एंड यूरोज में.
Hmm,
ये assumption important है कि वो दोनों भी लाइक पैरेलल है इनिशियली.
got it.
एंड दिस took me the entire day. Nice. No, man, this is not easy. So, well, it was fun. After I understood it, it was fun. Yeah. Well, I will mute myself and get back to it. I will see by
Okay,
11. I'm tired already.
okay.
Yeah, steady, man. Oh, by the way, uh, I will suggest to listen to this music. One sec. No, 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 no. Where did I post it? Oh, that's you. Okay, go to kinematics. I guess I was in kinematics.
Because there are three coupled angles when you know information about the single person going individually to solve the angle G, three coupled angles you want to look at the sides. Both sides by okay.
Yeah. By the way, try this. Lo-fi and like while sitting, this is true. It is good, honestly. If you watch anime, you will also like it more. You will like it even more.
Uh, I would, but I don't think I can do this on stream though.
Ah, fine, fine. Try it afterwards.
Yeah,
Some day later, yes.
yeah, yeah.
Yeah.
Sure.
Since we don't know the way get
Fusion plus RPY robot. Fusion plus. Why is this so hard? This partition plus RPY. For partition. Yeah, as simple as this. Then hmm. Uh, PSPY PZ is determinable, obviously. And for the orientation, we need this shit, specifically NOA as minus sin theta, this and this. Ah, so find the necessary RBY and its own displacements. Mm, Okay, this is Linux. This was also determined, but then how the hell do I find this value? Oh, makes sense. What?
Yeah, I don't.
So,
गर्मी है अपने काम पे तेरा स्ट्रीम है
mm, rotation alpha about z axis for the cylindrical coordinates does not affect x-axis. Mm, mm, does not affect the a axis. Okay. Parallel to Z. As a result, the rotation of the about the axis will cylindrical coordinates are along x-axis, rotation of alpha. Okay. So translation of r along the x-axis and meaning coordinate frame was initially here, it was moved along the x-axis, then it was rotated about the z-axis. That's not really sit with me. So they mean the rotated the position vector. I mean, I guess that what rotating about the reference frame means. So, hmm.
Now it makes sense, kinda. Alpha about the z-axis does not affect the a-axis. I guess, yeah. As a result, the orientation of phi a about the a-axis for RPY will simply be added to the rotation of alpha phi a about the axis. Simply we add it to alpha. What the fuck? Rotation of alpha a about the a axis. Simply alpha. Stand 26-degree angle is found for alpha is a summation of phi plus alpha. The solution from example. Contemplating. Robot with fixed joint variables. Position group and the orientation group displays the rest center in space. Position group represents the tool at the rest by rotating about the rest's own position. The full pose of an effector relative to the base is just the position transform followed by the orientation transform. Hmm.
Yeah, I guess. Both the sides are known for the reason being this orientation is done relative to the frame itself. Both sides are known for 4 by 4 matrices. So in principle, you just equate entries and solve for the unknowns. Same idea as every inverse kinematics example we've done so far. Yeah, this cylindrical transformation itself contains a rotation about alpha. About the base, the axis that's obviously around the angle is the difference extending above A and above E. So the rotation part of the right hand side is actually uh, no, alpha is tangled up with three RP1 angles inside one combined rotation matrix that four unknowns fighting over three independent rotation equations. I think I need to write this down. Sample 2.22. We have a given transform as is this visible though?
Huh. Mm, and reflector. Hmm. Cylindrical transform R and L multiplied by RPY phi A phi 0 phi N. Hmm. Zen. This pure translation uh, contains rotation about, rotation by alpha about z-axis. Mm, so the rotation part of the right hand side or total is actually rotation, and then the RPY alpha 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 n. Now alpha is tangled up with three RPY angles inside one combined rotation matrix. That's four unknowns fighting over three independent rotation equations, not solvable in the usual way. Mhm. Hmm.
Question by or and then question about then translation by L. The coordinate frame NOA is rotated as such, rotated upwards, but because of that, the axis remains parallel and this would be the resulting n-axis and the o-axis would be somewhere around along this. So geometrically, because the Z and A remain parallel for cylindrical transform, rotation about Z is essentially rotation about A. Only for the orientation of F and I. That's it. Forgot to say that. Yeah, so we are taking this.
Hmm. Hello.
I got sidetracked. Oh, it would have been really cool if I could really build a robotic arm for my phone. I will take rest in a few minutes. I just want to solve this particular question that I'm stuck on for so freaking long. Geometric shortcut. Oh, so alpha about a effectively is just alpha plus phi a. Rotation alpha, rotation phi a about NOA about the z axis. Yeah, the rest should be pretty straightforward because 4.24 is our cos alpha and 2.65 is our sin alpha. That gives us alpha is as 8 and 2.65, 4.24 as 32 degrees. Therefore, y is 6 degrees. Oh no, minus 6 degrees. And then R is 2.65 over sin alpha, and that's 0.53. Dz is just L, that is 6. And then phi O is a tan 2 of minus nz comma this shit. Like phi O is just the angle between nz and something. Something for sure. Can't really simplify that. So as 75 degrees. Similarly, phi n is 42. Guess we have all the parameters. Like these. These. Phi O and then phi n. Yeah, these are the RPY parameters, and alpha R and L are the cylindrical position parameters. Euler angles are similar to RUI except that the last rotation is also about current axis. Eh, I don't understand. I don't understand. Huh? Those are given Euler's angles at an above the current moving frame. Non-repeated Euler representation and oh. Uh, 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 uh. This is also about the axis. What about A and then what about theta and also what about Y? Why? Why? I don't think I can process this right now. Okay, Zito. Bye bye.